So the Kaplan-Meier curves. So the Kaplan-Meier estimator is a non-parametric method that usually used for estimating survival function from observed survival times. So the Kaplan-Meier is also known as the product limit estimator or the survival curve, and it handles sensor data naturally. So this is a non-parametric method and it's a very simple method for survival analysis. And it has various names, so that's product limit estimator, KM curve, or survival curve. This is just the basic survival analysis you can conduct on any survival data sets, and usually handles sensor data naturally. So this is just the formula for the Kaplan-Meier. So you can see this, we have multiplication. This is DI is the number of events at time t. So let's say at time 5, how many people experience that particular event, and NI is the number at risk just before time t. So at 5 hours, how many people were at risk just before that particular 5 hours? So how many people will remain before that 5 hours? So this is just a multiplication of all of this. So we're going to be doing this for each particular time. So this is the product of all conditional survival probabilities. So this is this survival table now. So I'm going to explain the survival table. So you can see that at time 0, the number of those at risk is 10, and the number of those that died is 0, and the number of those that were censored is 0. So which means survival probability is going to be 1. Because based on the formula, the probability of those that died is 0 divided by 10, which is 0. So we're going to be saying 0 here. 0 divided by 10, then 1 minus 0 is going to give us 1. So that's why we have 1 here. And at time 3, which might be 3 hours, let's say at hour 3, the number of those at risk was 10, the number of events is 1, and the number of those that were censored was 0. So always know that censoring is not usually accounted for. We only account for number of events and censored, and number of events and those at risk. So even have a value in censoring, we are not going to calculate it. So 1 divided by 10 is going to be 0.1, and 1 minus 0.1 is 0.9. So that's why we have the 0.9 here. But don't forget that survival probability is a product of conditional survival probabilities. So we're going to become multiplying it with the previous survival probability to now get the current survival probability. So 0.9 times 1 is going to be 0.9. We also have at time 5 hours, the number at risk is 9. The number of events is 0. The number of censored is 1. So we have 0 divided by 9, which is 0. Then 1 minus 0, which is 1. So that's how we have 1 here times 0.9. We have 0.9. Then at hour 7, we can see that the number of risks is 8. The number of events that those that died is 2. Then the censoring is 0. So we just say 2 divided by 8. Then we subtract 1 minus 2 divided by 8, which is going to give us 0.75 times 0.9. We're going to get 0.675. At time 10, the number of risks is 6. The number of events is 1. And the number of those that are censored is 0. We're now going to subtract 1 divided by 6 from 1. And we multiply it with what? Our previous probability, which is 0.675. So our final survival probability is going to be what? 0.562. So the survival probability, the probability of patients surviving at each time is these values that you can see in this table. So how do you interpret the KM curve now? We have what we call the KM curve, which I will soon be showing. So just know that the y-axis usually is survival probability, and it's from 0 to 1. It can't exceed 1, just like probability. And the x-axis is usually the time. Then we have what we call the step function. So it drops at a particular event. You are going to see it looks like a step, whereby it drops at a particular event, the curve. You have the vertical tick marks, which is censored observations. Then we have confidence band that show uncertainty. So when you have a survival curve, what are the key things you should try and look for? You should try and look for the median survival time. Also the survival at specific time points. And the shape of the curve, it should be steep and be a very gradual decline. And also the comparison between groups. So the median survival time is the time at which 50% of the subjects have experienced the event. So it's not the middle of the graph or the middle of the curve, but the time at which 50% of the observations have already experienced an event. So that's what we call the median survival time. So you read it from the KM curve. Where do you have your survival probability to be 0.5? So that is your median survival time. So it's usually more robust than the mean survival. So instead of taking the mean survival, take the median survival time. So it's usually more better. And maybe undefined if less than 50% experience an event, which means we might not actually have it defined if we have less than 50% to have already experienced an event. So let's say the number of people that died was not up to 50%. So it's undefined and usually preferred in medical literature. So if the curve never drops below 0.5, then median survival time is not actually reached. So if you look at this particular graph now, this is the graph of lung cancer patients. So this is the overall survival of lung cancer patients. So if you look at it now, we have our survival plot now. We have on the x-axis the time, which is in days, and we have on the y-axis the survival probability. This survival curve now, you can see the way it is declining also with a step. You can also see some of these ticks which indicate sensory at those particular time. Then if you look at it now, you can see our survival probability. These are median survival time now. Is where our survival probability fall, which is 0.550%. You can see it's around this area. This is around 300. So our median survival time is 300. If you look at it now, you can see the number of at risks at each particular time. You can see how decreasing they are until only just 2. We have only just 2 that remained at risk. So you can see at the end of the study, only 2 remain at risk. This is how the survival plot looks like. So we have the confidence intervals for Kaplan-Meier estimates. How do you come up with your confidence intervals? You can use 3 methods. Either use the Greenwood's formula, or use the log-log transformation for CI construction, or use the plane or log transformation. So R, when you want to get your survival confidence interval, when you use Kaplan-Meier curve, you can get it automatically. So wider confidence intervals occurs when you have fewer subjects at risk, or more censoring, or later time points. So in a situation where you have fewer subjects at risk, more censoring, and later time points, then it's possible you are going to experience wider confidence intervals. So comparing survival curves. So when comparing multiple groups between A and B, what do we do? So you can either use visual comparison. We plot various KM curves on the same plot, or non-overlapping CIs. So confidence intervals, we have various methods for calculating confidence intervals, which R can actually automatically give you. We have the Greenwood formula, we have the log-log transformation, we have the plane or log transformation. There's also situations whereby you can experience wide confidence intervals of your survival time probability. So this is whereby fewer subjects are at risk, or you have more censoring, or you have later time points. So anytime you have these 3 scenarios, it's possible that your confidence intervals is going to be wide. So comparing survival curve, how do you compare survival curve? You can compare survival curve through visual comparison. That is, you separate visual Kaplan-Meier curves on the same plots, or non-overlapping confidence intervals suggest difference. And also crossing curves indicates non-proportional hazard. You have like 3 Kaplan-Meier curves on the same plot now, and anytime you see that these curves are not overlapping, so it suggests that there is actually difference between these 3 groups. Let's say between 2 gender, male and female, you have 2 curves. If you see that they do not overlap these particular curves, then we can now say that it suggests that there's a difference between them. But if they overlap, it suggests that there is no difference between them. So crossing curves indicates non-proportional hazard. So anytime you have a crossing curve, that is a curve that instead of overlapping, it crosses, then you have non-proportional hazard. So statistical tests they can also use to compare survival curves is log rank tests, or tests whether survival distributions differ. So if you look at this curve now, you can see we have overlapping curves, and not just overlapping, we also have crossing, like that crossing. You can see them. So if we look at this now, let me show you the difference between a crossing and an overlapping curve. So this survival plot now, we are using comparing various age groups now. 3. You can see the green is less than or equal to 60 years, the blue is 61 to 70 years, and the red is 70 years. If you look at these particular curves now, you can see that the green is actually overlapping with the blue, but at a point it crosses with the blue. So you can see the red is mostly overlapping, not crossing. So, and you can see from that place, we say that when they are overlapping, it means there's a difference. So it means there's a difference, statistical difference between greater than or equal to 70 years compared to also other age groups. So these are the number of risks at risk for each particular age group, and you can see the time below also for each particular age group. So this is the example of using the Kaplan-Meier curve for comparison. So what are the various assumptions of the Kaplan-Meier method? So first of all, the sensory is independent of survival. What do you mean by sensory should be independent of survival? It means censored objects should have the same prognosis as those that are continuing. So which means that their conditions should be the same with those that are continuing. So survival probabilities should also be the same for early and late recruits. So there should be no time trends in underlying risks, and the events should occur at specified times. So there should be no measurement error in event times. So these are the various three assumptions. So first of all is that censoring should be independent of survival, and that means you should not have anything that's affecting censoring. So even though the Kaplan-Meier method is a very good method, it has some limitations. One of its limitations is that there are no adjustments for covariates, so it cannot control for confounders. So I already talked about confounders in regression. So one of the disadvantages of Kaplan-Meier method is that I cannot adjust for confounding, and that's why we'll be looking at the Cox regression later on for multivariable analysis. The Kaplan-Meier method is descriptive only. That means it does not quantify effects. It only describes. We don't know by how much a particular covariate is affecting the survival of individuals in the study. Also, it is limited to categorical comparison, so you cannot use continuous variables. If you notice, we're only using age. For example, in that particular survival curve, we compared age, we can compare race, but out of continuous variables, how would you compare survival times in terms of continuous variables? So this is one of the limitations. It also assumes independence, that is issues with competing risks. So however, the Kaplan-Meier method assumes independence. We have various issues with competing risks and small sample problems. It's usually unstable at tail of distribution. So when you don't have a large sample, you're likely to face issue of instability at the tail of the distribution. So when do you use Kaplan-Meier curves, what are they good for? If you're trying to describe survival experience, you don't want to go deep, you can use the Kaplan-Meier curve. Also, as an explanatory analysis method, is also a good way of explaining your survival in your data. If you also want to compare 2 to 3 groups visually, Kaplan-Meier curve is a good alternative. If you want to report outcomes in a clinical trials also, and also you want to communicate with non-statisticians, Kaplan-Meier curve is also a very good option. So what is it not ideal for you to use the Kaplan-Meier curve? If you have many covariates that need adjustments, you need to find an alternative. If also your sample size is small and you have a lot of censoring, then you need to find an alternative, because I told you earlier on that the median survival time is going to be undefined if the number of events is less than 50%. So in these situations, you need to find an alternative, and the Kaplan-Meier curve might not be the best option for you.